Hello everyone, I'm Tim Northover from Apple, and I'm going to tell you a bit about how we brought 32-bit pointers to ARM64 while maintaining compatibility with existing software. So anyone that's hung around the LLVM mailing lists or IRC for a while will have seen someone go away vaguely disappointed when they're told that LLVM IR isn't like your classic JVM. You can't write it once and run anywhere. You should expect the IR to contain quite a lot of target-specific details. But this is only true to a sort of limited extent, or to the majority of the extent. If you can carefully define both of your ABIs and platforms at the same time together, you can overcome this and make it so that you can take IR written for one ABI, in our case ARMv7k 32-bit ARM, and feed it into the ARM64 backend, also targeting an ILP32 platform, and produce compiled output that's compatible with all the existing libraries and frameworks and software. So for the rest of the talk, I'm going to start off with going into some details about exactly how LLVM is target dependent and what you have to overcome to make this kind of scheme work. Then I'm going to give a few more details about the slightly more technical issues we had to overcome. And finally, I'll talk about how we managed to make the ILP32 scheme work in LLVM's selection diagram for structure, where there's a certain impedance mismatch that makes things a bit tricky. So starting with the IR compatibility, there are sort of two main areas where LLVM IR is target dependent, and a host of much smaller issues stretching out into the whole platform in the end. Most notably, at the top of every module, there's this data layout string, which gives the alignments and alignment requirements of fundamental data types like native integers, floats, vectors, and the size and alignment of pointers. Now, you might hope, if you were lucky, you could change this when you were retargeting LLVM IR for a different processor. At the same time, you change the target triple, and everything would work. But unfortunately, this doesn't quite work, because while LLVM will use the new data whenever it calculates a get element pointer for struct offsets and array offsets, even allocas, Clang has already evaluated virtually all of your size of expressions in mallocs, for example, and embedded them into your module as a plain constant that you don't even know came from a size of, let alone the struct or type it was evaluating. So there's no way after the fact you can hack this up to restore sanity. As well as the fundamental alignment things for basic types, bit fields are woefully underspecified by C and C++, so every platform has basically decided to make its own take on what the designers really meant here, and they've all disagreed completely with each other. You've got quite a few decisions. You've got to decide, for example, if you've got a short bit field, is that allowed to overflow a short word boundary? Some platforms say yes and will just carry on. Others say no and will bump the field up a little bit further to an alignment boundary if it would do that. Zero-width bit fields can either be completely ignored or they can be treated as hints to align the next field to a particular value, or occasionally just to align it to 4 bytes, because why not? The other main way in which LLVM IR is target dependent comes about from function calls. And Clang, and any front end really, that wants to follow a specific set ABI, which most do, has to decide with deep knowledge of what the backend will do with its function prototypes, how to map its native types, Clang's structs, C++ classes, and so on and so forth, into usually a single LLVM type that will then get interpreted by the backend and put into registers or on stack as appropriate. Most of the time, this is just a single one-to-one mapping. A sort of struct of 2 ints goes to an I64 or something. But some backends have schemes so complicated that the Clang has to literally iterate through arguments one at a time and know exactly what argument number it's dealing with and where this parameter is going to go to be able to assign it properly. And to help it in this, as well as changing the LLVM type, it can insert padding variables that are completely ignored by the caller and callee, but they're just to consume resources in the function parsing world. And it's got a bunch of attributes it can attach to each function argument. These essentially act as sort of hints to the back end on how it should treat this argument specially. The most common is probably byval, which goes on a pointer argument. And instead of meaning just pass this as a pointer, it means copy the actual object onto the next available stack slot. So I'll give a few examples of how this works out in ARM64 now that will become a bit more relevant when we discuss compatibility later. So this first struct has a size of 8 bytes and an alignment requirement of 8 bytes too. And this works out perfectly nicely in ARM64. It gets passed as an I64, which LLVM knows will take up a general purpose register if one's available for function passing, and if not, will take up a 64-bit aligned stack slot, and everything works out fine. This second struct is similar. It's the same size, 8 bytes, but only has 4-byte alignment requirements in general. Except there's a special exception for parameter passing, which makes it equivalent to the above struct on ARM64. This isn't true on ARM32 platforms, which is why it becomes especially relevant later. Both of these two first structs are key for later. But going further, this struct has sort of 32 byte size, and ARM has decided that this is too big to be worth passing in actual registers. So it's expected that the caller will allocate somewhere on the stack usually and pass just a pointer to the argument. And Clang implements this by, there's a function called getIndirect, which is a special hint that says pass a pointer to this and do the magic behind the scenes. On the other hand, this very similar looking struct, it's the same size, same everything except it's floating, and there's a concept of a homogeneous floating aggregate, where presumably because of different trade-offs in register sizes, register pressures, ARM's decided that this is worth passing as a struct, and that's implemented by passing it in LLVM terms as an array of 4 doubles, which the backend will then keep together if it would mix between registers and stack and just generally knows what to deal with in a fairly intelligent manner. So those were the two big ways in which LLVM is target dependent. There's lots and lots of smaller ones. I mean, I expect everyone knows that C++ allows you to override functions. You can have 2 functions with the same name but taking different types. And this is implemented behind the scenes by encoding the type of each parameter into the function name in the LLVM module. And it's called mangling. And this makes it particularly important to be consistent whether int32t is type-deffed in your studint.h header to an int or a long, even though they're notionally the same 32-bit type. Other barriers we had was that ARM's got a pretty much platform-independent set of headers defining SIMD intrinsics. And these are shared between all ARM platforms, but not by the time they're output from Clang. Clang has to translate these into target-specific calls, which will only work on the single backend they were headed for. So we had to add a pass in our scheme to translate these into ARM64 equivalents. And obviously, if you're going for compatibility, nothing but the most trivial of inline assembly. Maybe you could get away with a mov and an add, but not much more can be translated from one machine to another. And finally, for an idea of what came out from further out in the platform, C's got this set jump long jump function for implementing jumps between functions. And that takes a type called a jump buff T, where the platform's supposed to save all the registers that might need to be restored when the final jump gets back here so that execution can continue. And this buffer has to be big enough for all the registers that might be saved. So in our case, when we were implementing ARMv7k sort of a few years ago, we had to make sure this buffer was big enough for all ARM64 registers that would be needed last December or something. So the idea was, what we decided to do back in 2015 or something was to design both ABIs together so that this scheme could possibly have a hope of working. And we wanted them to be as natural as possible with other ABIs for ARM64 and ARM32. But where compromises had to be made, we decided that we wanted it to be the ARMv7k, the 32-bit ABI that took the hit, because we expected the 64-bit one to be around longer. And because of this, there were some implications for ARMv7k. wherever there's a sort of heuristic for a size or something, the decision that's been made looks suspiciously like it was designed for a processor with twice as many registers that are twice as big. I mean, most notably, the threshold where structs decide to become passed indirectly is only 4 bytes on most ARM32 targets, but is 16 bytes on ARM64 and our ARMv7k ABI, because there was no way we could make it the 4-byte sized originally and continue to produce sensible output assembly in the ARM64 world that was compatible. And where the rules for homogeneous aggregates that I mentioned earlier differ, there again, they take the ARM64 thresholds for when it's worthwhile. But despite all that, there was some inevitable hits that ARM6432 had to take. I mentioned earlier the SIMD intrinsics, but there are other ones coming from things like byte swap built-ins in Clang and some strange Objective-C annotations that just you can't change on the ARMS32 side, so you have to translate them with a separate function pass or even module pass on the ARM64 side before you actually proceed with compilation. And to make function calls work, we had to give, in the end, special handling for an LLVM IR array type in a way that I'll describe now. So if we look back at these two structs that we saw before, they're the same two, both size 8. This time the first one has alignment requirements of 4 bytes, and the second has alignment requirements of 8 bytes. And ARM ABIs have this strange feature where even the registers get aligned if possible. This is, I think, originally to make var args handling easier. You could just push the registers before the stack and pretend they weren't there after the original call. But the result is that the first of these structs should be passed in R1 and R2 in this function, and the second should go in R2 and R3, completely ignoring the existence of R1. So in ARM64 world, this works out fine. They both get passed as an I64, as I said on the previous slide, and they'd both get allocated to the X1 register as they should in any sensible ARM64 ABI. So what if we tried to do this same scheme on the v7k world, if we emitted the same code as ARM64 was expecting? Well, in that case, we'd take a hit on the v7k ABI, where the first struct would be passed as if it required 8-byte alignment, and so it would also skip R1 for even more obscure reasons than the original one. So that's not really viable. Alternatively, we could say that the front end should handle it, all the alignment requirements, and that the back end should just use the next available resource, whatever it is. In this case, Clang would be expected to insert one of the padding arguments I mentioned before, this I32 in the second case, that would consume R1 on the ARMv7 implementation, leaving R2 and R3 available for the struct. But of course, that argument's still there on ARM64 and would eat up the X1 that the struct is expected to be passed in. So finally, you're sort of led to the conclusion that these two have to be passed as two separate types. And naturally, this would, and is in other ARM targets, an array of 2 ints for the 4-byte alignment requiring one, and an I64 for the other. Normally, this wouldn't actually work because ARM64 only gets to see 2 separate I32s mostly. The split up happens very early on in selection DAG process, and so it would allocate this argument to 2 separate general purpose registers, which isn't what we want at all. But this is sort of mostly just a hint, or mostly just a guideline, and actually you can modify the backend to take these 2 halves, recombine them back into a single register, and generate code like that. What you get isn't as efficient as the native code, but it is binary compatible, which is the important thing for us. In addition to that kind of unavoidable impact on ARM6432 that we knew we had going in, there was avoidable impact, otherwise known as bugs, we discovered later on, but not quite too late to break the whole project. Most annoyingly, I still got bit fields wrong. I knew going into the entire thing that there'd be a problem and that there were dozens of handles to tweak them, and I thought I got them right. But a couple of years later, it turned out I hadn't. And so we had to fix ARM6432 with a, in my view, not so good ABI so that it would work. Most of the other issues came from, I think, focusing too much on Clang as a front end, despite having Swift in-house, really. For example, Swift has some runtime functions that return a pointer and an int pair, and it thinks that it knows how Clang's going to generate these, or at least that it thinks that what it generates is compatible. And mostly it was, but it's not in this scheme. So one half of the function is declared or defined as returning an I64, and the other as a 2 by I32. And we could have implemented the same kind of array hack we used for function parameters here. But since we decided there were only a closed set of about 13 functions like this, we added another pass to our backend to translate or fix up each of these call sites when we were ingesting IR. The other front end that was a problem was .NET, which no one inside Apple had ever really seen. But it turns out it uses a preserve all CC calling convention, which is basically not supported anywhere on ARM, doesn't do anything, well, it must do something, but doesn't do what it claims. But it noisily fails on ARM64, so we had to disable that warning and make sure it was at least doing a calling convention that was self-consistent. So I'm going to talk a bit about how we implemented the 32-bit pointers now, and especially the extra issues we had compared to the x86-64 case, where on x86-64, you still have 32-bit addressing modes. You can still tell all your load and store instructions to perform their addressing arithmetic at 32 bits and wrap it round, which fits in well with LLVM. On the other hand, on ARM64, all addressing calculations are done at 64 bits, no matter what you do. And so this is a potential problem for 32-bit pointers. However, it's only a theoretical problem because in practice with C and C++ and all other languages I know about, no one actually cares about wrapping when you do pointer arithmetic. It's just not supposed to happen. Checked languages check it. C and C++ say it's undefined behavior if you do it. So this function here, for example, which takes a base of an array, a 32-bit offset, indexes into the array and returns the element there, it can compile down to just a single function in ARM64, or even with 32-bit pointers. There's a single instruction that will take the base of the array from x0, the 32-bit offset from the W1 register, sign extend it as the language reference says you should do for get element pointers. It's defined, that's how it treats subsized indexes. Shift it left by 2 so that we're stepping in chunks of 4 bytes rather than 1, perform the arithmetic and load the result into the correct return address, leaving just a ret instruction afterwards. Unfortunately, things aren't so good with a naive implementation based on LLVM selection DAG, which I've got a small picture of up in the corner here, where all the arithmetic in the previous calculation is done at a 32-bit level. And the first problem you hit is, okay, so base is sitting there in a nice W3 register, 32 bits. What's in the high bits of that register? And LLVM is pretty much doesn't help you out there. As far as it's concerned, those bits don't exist. In almost all cases, there'll be 0 because almost all ARM64 instructions that actually do 32-bit arithmetic zero out the high bits. But you might have done a 64-bit calculation there followed by a trunk, in which case they could be complete garbage that you have no control over. So usually you'd be okay, but it's very difficult to prove this. But suppose you had some oracle that could tell you if the base side was safe to use in the addressing mode. You've still got to answer the question, what should you do about the offset before adding it to the base? Do you 0 extend it or sign extend it? And unfortunately, this depends very much on the dynamic values of both the base and the offset if you want to avoid overlapping. If the base is a really high value, you almost always want to subtract the offset, so you should sign extend it. On the other hand, if it's a small value, you almost will always want to add it, so you should 0 extend it. And it turns out that even with no unsigned wrapping flags and so on, the only time you could really ever use the addressing modes in this situation is if you knew the offset was a compile time constant that fitted into one of the instructions. And when all this was implemented, we discovered that there was about a 10 to 15% compile time overhead. It was too early to really assess runtime overheads then, which we decided was unacceptable. So in the end, we decided we could solve this if we made pointers still be 64 bits in the selection DAG representation. Now that means that at every load of a pointer, you would zero extend it into those 64 bits and truncate it back at every store. Inbounds GEPs, which fortunately because of languages are sensible, represents about 99% of them, can be just lowered to plain 64-bit arithmetic where you treat the pointers as they are and sign extend the offsets as they come in. Wrapping GEPs, the very rare case, you have to actually insert a manual and Nortex FFFFF whatever to make sure that it does wrap after the calculation, but that's acceptable because there are so few of them, it doesn't really affect performance. And there are a couple of other operations that are special. If you've zero extended your pointers, you can't hope to do a signed comparison on them except for equality. Otherwise, you'll get nonsense results, so you have to retruncate before that in the DAG in a couple of places. And when all this was implemented, ARM6432 was actually pretty much on par with the plain ARM64 backend in terms of code size. There were occasional, very slight bloat from people using int pointer casts and back again, but that was pretty acceptable. So when we had these two ABIs, we had to sort of verify that they worked well, and not just the normal worked well, that's if not solved problem, well understood, working well on its own. We had to make sure that they worked well together, that our translation scheme from ARMv7k IR to ARM64 assembly was actually working and compatible. And this went in a few stages. First of all, we were able to build the LLVM test suite where we took random C or C++ file and either targeted it directly to ARM64 or via the ARMv7k ABI IR. And then any time a function call crossed a translation unit, they would be testing ABI compatibility. And this is what allowed us to spot the bit field bug back in Specs GCC test, which uses that. A little further along the line, we were able to do the same trick with system frameworks and libraries, and then if the system booted up and programs worked, we thought we were on a good track. It turned out this didn't find anything new, so we thought we were great for a while. And then we actually managed to test apps which contained a lot more Swift code. And when we compiled the real apps that we wanted to run on the final platform to ARM6432, we discovered this Swift runtime issue, but fortunately not too late that we couldn't fix it. And that's all for me. Does anyone have any questions?
Please use the mics if you have any questions, or if you need it brought to you, let me know.
So there is a draft ILP32 ABI published by ARM. Are you going to, so is it in any way compatible with the draft, the Apple's ILP32 ABI, and what do you plan to call it if it's not compatible?
So what we've got isn't compatible with the draft because of the adaptations we had to make to be compatible with the original IR slightly. But it would be very easy to extend the bulk of the work we've done to make an ABI that is compatible with the draft. It would just involve tweaking a few bits of calling conv.td table gen file. Yeah.
Are there any other questions? Okay, our next talk will start in about 10 minutes. Thank you, Tim.